Uh, Good afternoon, my dear grade 8 learners, and good afternoon to my colleagues. Today, I am going to do multiples and factors, and let's get started. You can move, Mr. Patrita. Yes, this is our presentation outline. We are going to look into a definition of terms. We are also going to look into the prime factorization of numbers. Again, we are also going to check how are we going to find highest common factor and lowest common multiple using prime factorization. And then lastly, calculating roots using prime factorization. You can pass, Mr. Potriter. Again. Right. We are going to look into the issue of what is a factor. Right. As you can see there, a factor of a number is all the numbers which can divide exactly into a number without leaving a remainder. You can pass that. So here are the examples of a factor. Factors of 18. We have 1, 2, 3, 6, 9, and 18 because if you take 1 and then you divide 18 by 1, you'll get 18. You divide 18 by 2, you'll get 9, and so forth. Again, we are going to also look into the meaning of a multiple of a number. Right. A multiple of a number, all of the numbers which the number can divide into without leaving a remainder. In other words, the multiples, we are having multiples, and then this number can divide into these multiples. So those will be the multiples of that particular number. In this case, we are talking multiples of 6. We have 6, we have 12, 18, and 24. And be aware that the multiples are continuing up to infinity because for us to have the multiples, we must multiply that number with natural numbers, and natural numbers are continuing indefinitely. Okay, Mr. Potrita. Right. And then we are also going to look into the issue of a prime number. A prime number is a natural number greater than 1 with only two factors, 1 and itself. These are the examples of prime numbers between 1 and 50. Okay. And then we also going to look into the issue of composite number because we are actually going to decompose them into the prime factorization. So a composite number is a natural number having more than two factors. And these composite numbers are all the natural numbers that are not prime numbers. So here is the example of composite numbers. And then we have the situation whereby we have to classify 0 and 1. As the explanation was clear to say a prime number must have two factors. 0 is not a prime number. 1 is also not a prime number because it is having only one factor, which is 1. 1, it is a universal number because it is a factor of all the numbers. And then we are going to actually decompose a composite number into prime factors. Right. As you can see there, we are having 180. This 180 is decomposed into 2 and 90, but 2 is a prime number. 90 is not a prime number. So therefore, we have to decompose 90 again into 2 and 45. And then you will realize that we have two factors of 2, and representing them in the form of exponents, it is 2 to exponent of 2. And then we decompose 45 into 3 and 15. 3 is a prime number. Yes. And then 15 is also a composite number. It needs to be decomposed. Therefore, we are having 15 as represented by 3 multiplied by 5. Right. And then this is another method of actually finding prime factorization of 180. As we can see there, we have 180. We have to look for the first prime factor. We divide 180 by 2, we get 90. We have to look for the prime factor that will divide into 90 again. And that prime number is 2. 2 divide into 90, 45 times. Now, we have to divide 45 with the next prime number, because now 2 doesn't divide into 45. The next prime number will be 3. So if we divide 45 by 3, we will get 15. Again, 3 is still dividing into 15, and then 15 divided by 3, it will be 5. And then we divide again 5 by 5, and then we will get 1. Once we see 1, note that we are done with prime factorization. And then we have to actually express our prime factorization in the form of exponents. You'll see why we have to actually do that. Right. Now we are going to use prime factorization to find HCF and LCM. Right. Here it is a question: use prime factorization to determine HCF and LCM of a number 840 as well as a number 1500. So we are going to use prime factorization. 840 divided by 2, it will be 420. 420 divided by 2, it will be 210. 210 divided by 2, it will be 105. And then now we cannot divide 105 because it will leave a remainder. We divide 105 by 3 as next prime number. And then we will get 35. And then 3 is no more dividing into 35. Therefore, we'll have to use 5 to divide into 35, and we will get 7. And then we divide 7 by 7, we get 1. So now we are done with 840. And then moving to the next number, which is 1500. The first prime number to divide is 2. And then it will go 750 times. 2 still goes into 750. And then it will go 375 times. 2 is normal dividing into 750 without leaving a remainder. Therefore, we use 3 as the next prime number. 375 divided by 3, it will be 125. And then 125 is no more divisible by 3. And then we use 5 as the next prime number. It will give us 25. And then 25 is divisible by 5 again. 25 divided by 5, we will get 5. And then 5 divided by 5, we will get 1. Now we have to represent them in the form of exponents. As we can see there, 2 to exponent of 3. It is because we are having 3 factors of 2. We also have 1 factor of 3. We have 1 factor of 5. We also have 1 factor of 7. Coming to this one, we have how many 2's? We have 2 2's, which means we have 2 factors of 2. We also have 1 factor of 3. We have 3 factors of 5. Therefore, we can be able to represent them in the form of exponents. Right. Now, we have to look for highest common factor first. For us to be able to find the highest common factor, we have to look into these 2 numbers that we are having. And then the reason why we were actually we actually have to represent these numbers in the form of exponent. It is because when we have to determine highest common factor, we have to check the bases that are common. We have to check the bases that are common, only common bases. We focus on only common bases. As we can see there, the common bases are 2, 3, and 5. But 7 is not common. So in other words, we are not going to consider 7. We will only consider the base 2, base 3, base 5. So in determining the highest common factor, we will only have to take the common basis with the lowest exponent. As you can see there, with base 2, we have exponent 3 and exponent 2. The lowest exponent between the two is 2. And then with 3, we don't have any problem. The exponents are the same. Therefore, we will just take 3 with exponent 1. And then lastly, we will take 5 with the lowest exponent, and the lowest exponent between 3 and 1, it will be exponent 1. So our highest common factor will be 2 to exponent of 2 multiplied by 3 to exponent of 1 multiplied by 5 to exponent of 1. If you multiply them, you will realize that the highest common factor of the 2 numbers is 16. I just want to repeat it. When you are looking for the highest common factor, you must take all the bases between the 2 numbers, all the bases that are common, and then you take them with the lowest exponent. And because I've emphasized that, for sure you will just think what is going to happen with lowest common multiple. Right. With lowest common multiple, we are just going to look into all the bases that are there, irrespective of they are common or not. You'll realize that 7 is the only base that is not common. We are going to take 7 also. But in this case, we take all the bases that appear between the 2 without repeating them. And then after taking those bases, we are looking for the basis that the highest base. No, the highest exponent, sorry. We are going to take this basis with the highest exponent. Like for instance, if you check the base 2, the highest exponent is 3. That is why we have taken 3 as the solution. And then we're also going to look into 3. For 3, we don't have any problem. It is 1 and 1. We just take 3 with exponent 1. And then with base 5, we have the lowest exponent as 1, the highest as 3. So we take them with the highest exponent. So in this case, the highest exponent is 3. And then lastly, we are going to take base 7. Base 7 is with exponent 1. We take it as it is. And then this gives us the lowest common multiple. If you can check, you'll realize that the lowest common multiple of the two numbers is 2,100. Right. And now we are going to calculate the roots using prime factorization. This is one of the questions that are not familiar, but we have to expose you to this such that if it happens that an examiner decides to actually assess in this, you will be able to deal with this. So now we are going to use prime factorization to determine the square root of 3,600. So firstly, we must find the prime factorization of 3,600, which now I think we know how to find the prime factorization of any number. Right. Remember, we have to look for the first prime number and check it if it can divide. And then if it doesn't, we go to the next one. So in this case, 2 is still dividing. Right. Now 2 cannot divide, therefore we have to check the next prime. The next prime is 3. It divide into 225. Also 3 divide into 75. But now 3 cannot divide into 25 without leaving a remainder. Then we have to look for 5. 5, it divides 5 times into 25, and then into 5 it divides once. Right, as you can see there, 3,600 is the same as 2 to exponent of 4, 3 to exponent of 2, 5 to exponent of 2. But remember, we are looking for square root, not 3,600. So we have to put square root under yes. So as we put square root on 3,600, we have to put square root also on the right hand side. Right. And then square root of 2 to exponent of 4, 3 to exponent of 2, 5 to exponent of 2 will be 2 to exponent of 2 multiplied by 3 multiplied by 5, because we divide all the exponents with root 2. So as we divide with 2, it will give us this, which is equals to 60, which is equals to 60. My dear learners, thank you very much for tuning in. Even though I had some challenges from my side, but at least the presentation went through. And thank you very much for tuning in. And also thank you very much, Mr. Potgieter, for coming to my rescue.